Welcome to this explainer on CISSP Domain 3, Security Architecture and Engineering. I am absolutely thrilled to guide you through this material today. Look, if you're a focused learner preparing for the exam, you know that Domain 3 can honestly feel like a massive mountain of abstract theory. But today, we're going to break it all down. We're putting on our managerial risk lenses to take a highly structured deep dive into the blueprint of secure system design, core security models, and the evaluation frameworks used out in the real world. Get ready to elevate your exam mindset.
Okay, let's look at the agenda for today. 1. Secure system design principles. 2. Techniques for ensuring CIA. 3. Core security models. 4. Advanced security models. 5. Common criteria and ATO. And finally, 6. Information system security capabilities.
Section 1. Secure System Design Principles. Establishing the baseline of architecture.
Before we get into the heavy technical how of security, we absolutely have to nail down the why. Why do we architect systems the way we do? Security shouldn't just be tacked on at the end, right? It has to be an integrated element of the system's design from day one. One of the very first architectural choices you face is between open and closed systems. Open systems are built on industry standards and open APIs. They are fantastic because they integrate so easily with other systems. But here is a crucial CISSP exam mindset note that ease of integration, legally and operationally, presents a much larger and far more predictable attack surface for your organization. Closed systems, on the other hand, use proprietary, unpublished standards. Sure, they are much harder to integrate, which can be a headache, but that lack of open APIs means they are generally much harder to attack directly without highly specific, customized knowledge.
Now, reality check. No system runs perfectly forever. Things fail. But when a failure happens, we have to intentionally design exactly how the system responds. Take a look at this table summarizing failure states. In the physical world, your ultimate priority is almost always human life. If power gets cut to a building, electronic doors need to fail safe or fail open so people can quickly escape. But in the digital world, that priority completely flips to protecting assets. A firewall losing power shouldn't suddenly drop its shields and allow all traffic through. It needs to fail secure or fail closed to protect the network's confidentiality and integrity, even if it means totally sacrificing availability in the process. So, keep this strict legal and operational threshold in mind for the exam. The physical world prioritizes human safety, while the digital world prioritizes asset protection.
Moving on to modern network architecture, we've got to talk about zero trust. That old-school perimeter model, where we just sort of trusted everything inside the firewall, that is completely obsolete. Zero trust replaces all of that with a simple mantra: never trust, always verify. You literally have to operate with an assume breach mentality. This means stripping away default trust and bringing in strict internal microsegmentation thresholds, where every single access request has to be authenticated, authorized, and encrypted. This stops an attacker dead in their tracks, preventing them from moving laterally even if they do manage to get inside.
Section 2. Techniques for ensuring CIA. The mechanics of enforcement. Let's take a look at the progressive stack an operating system uses to protect memory spaces. First up, we have confinement, which you might also know as sandboxing. This restricts a process so it can only read from or write to specific, explicitly allowed resources. Step 2, we establish bounds. This is where the operating system sets strict logical memory limits, defining the exact area where that process is confined. And finally, step 3, by enforcing those bounds, we achieve isolation. Isolation guarantees that if one process suddenly crashes or gets compromised, it won't interfere with the operating environment or go snooping in the memory of another application.
So all these operating system mechanics make up what we call the Trusted Computing Base, or TCB. The TCB is basically the subset of your system, the hardware, the software, the controls that you explicitly trust to enforce your security policy. And it's wrapped in this imaginary boundary called the security perimeter. But listen up, here is a massive CSSP exam mindset note. You absolutely must understand the difference between the reference monitor and the security kernel. The reference monitor is just an abstract, logical concept. It's the pure idea of validating an access request before granting it. The security kernel, on the other hand, is the actual, practical, testable implementation of that concept in your code and hardware. Simply put, the monitor is the theory and the kernel is the reality.
Section 3. Core Security Models. Navigating Theoretical Architecture. All right, we're hitting the cognitive peak of this explainer. I really need you to put on your managerial risk lenses right now as we navigate some of these heavily tested theoretical frameworks. First up is the Bell-LaPadula model, originally created by the Department of Defense. This model cares about one thing and one thing only, and that is confidentiality. It relies on two main rules. The simple security property says no read up, meaning you cannot read data that is classified higher than your clearance. Then there's the star security property, which says no write down. You cannot take top secret data and just paste it into an unclassified document. Here's a great mnemonic anchor for test day. The star property always relates to writing. Writing down is forbidden so secrets don't leak out. The only exception here is for a trusted subject who can actually bypass that star property to do valid document declassification.
So the crucial point to grasp here is how Bell-LaPadula contrasts with the BIBA model. While Bell-LaPadula is all about confidentiality, BIBA focuses strictly on integrity. And here's an easy memory hack for the exam. The word BIBA has an I in it, and so does integrity. Plus, BIBA's rules are the exact mathematical inverse of Bell-LaPadula's. The simple integrity property is no read down, because you really don't want to read unvalidated low-integrity data into a high-integrity document. And the star integrity property is no write up, meaning a lower cleared subject cannot modify higher-level data. Just remember, simple is always about reading, and star is always about writing.
Now, another major integrity model you need to know is Clark-Wilson. But unlike BIBA, which uses a strict lattice of classification levels, Clark-Wilson uses an access control triplet: subject, program, and object. Basically, a subject can never directly touch the object. They have to go through an intermediary program or constrained interface. For your exam mindset, keep in mind that Clark-Wilson is tailor-made for commercial environments. It uses well-formed transactions and really strict separation of duties to protect commercial integrity. It ensures users can only do what they're authorized to do through heavily controlled software portals.
Section 4. Advanced Security Models, Specialized Use Cases.
Building on those core foundations, security engineers developed specialized models that handle dynamic access, state transitions, and specific administrative tasks. Let's do a quick rundown of the advanced frameworks you need to know. The Graham-Denning model focuses on securely creating and deleting subjects and objects. Then there's the Harrison-Russo-Ullman, or HRU model, which deals with the rules for editing access rights inside a matrix. The state machine model simply dictates that a system must stay completely secure during any transition from one state to another. But the one I really want you to focus on is Brewer and Nash, also known as the Chinese wall model. This model dynamically alters a user's access based on their prior data activity to avoid a conflict of interest. It basically builds an ethical or legal wall. So if an analyst looks at data for company A, the model dynamically steps in and blocks them from seeing data about competitor company B.
Section 5. Common Criteria and ATO, Real-World Evaluation. So how do risk managers actually evaluate, trust, and legally authorize these insanely complex systems out in the real world? Well, we use the Common Criteria. It's an international ISO standard for evaluating the security features of IT products. It uses evaluation assurance levels, or EALs, that go from 1 to 7. EAL 1 is just basic functional testing. EAL 4 means rigorous commercial development practices. This is pretty much the benchmark for standard enterprise software. And EAL 7, that is the absolute highest level of formal verification, reserved for extreme high-risk scenarios like national security. But hey, here is your due diligence exam mindset note. EAL ratings evaluate the vendor's product in a vacuum. Buying an EAL 4 firewall does absolutely nothing to guarantee security in your specific environment if you go and misconfigure it. Once a system is fully evaluated, an authorizing official has to formally accept the risk before the thing can actually go live. Under the NIST Risk Management Framework, this is called an Authorization to Operate, or ATO. Getting an ATO is effectively hitting a legal and contractual threshold that proves the risk is managed to an acceptable level. Now, an ATO is usually valid for 5 years, but remember this crucial detail. It can be instantly revoked if the system suffers a significant security breach or goes through a major configuration change. The authorizing official always retains the power to issue a denial of authorization if the risk ever becomes unacceptable.
Section 6. Information Systems Security Capabilities. Hardware Defenses.
Now, it's pretty fascinating to see how all that theory about bounds and isolation actually meets the physical hardware. Memory protection is a core OS capability that stops a process from interacting with unassigned memory spaces. So why does this matter? Just look at vulnerabilities like Meltdown Inspector.
Modern CPUs try to predict future instructions to speed up processing, but when they guess wrong, they don't always clean up their mess, which leaves data remnants sitting behind in memory completely unprotected. Having robust memory protection is absolutely vital to stop these hardware-level data remnants from being scooped up by malicious processes. Another totally vital hardware defense is the Trusted Platform Module, or TPM. A TPM is a dedicated hardware cryptoprocessor chip installed right onto a computer's mainboard. It basically acts as a hardware root of trust. It securely manages, stores, and processes digital encryption keys. By keeping those keys physically sealed inside a chip, rather than just floating around in the operating system's software memory, you are establishing a strict physical boundary, and that is a clear due diligence requirement for protecting against digital key theft. To wrap up this explainer, I want to leave you with a bit of a thought experiment to test your exam readiness. Imagine a commercial database strictly enforces separation of duties, and it prevents users from directly modifying data by forcing them to use a very specific, constrained application interface. Which theoretical security model are you looking at, and why is identifying that exact model critical for a risk manager who's performing due diligence? Think about that access control triplet we talked about. Think about commercial integrity. Getting yourself into this analytical mindset is exactly how you're going to conquer Domain 3 on the CISSP exam. Thanks for diving into this with me today, and keep that focus sharp.